Hello, Dr. Vanderlinde, can you hear me?
Yes, hello.
Okay, perfect. I'm glad you
Hi.
found the link. Just replied to your email and
Yes, sorry for the last minute panics. The place didn't open up until like 5:02. So
no worries. I know the link on the official page doesn't open up until 5 minutes for the audience, but
okay, great.
using the link you can get it. But anyways, we're all good. The main stage is still currently active, and there's still a Q&A being done there, so people will trickle in the next 5-10 minutes or so.
Yep, no worries.
Do you want to try sharing your screen if that works?
I would love to, but I don't see any option for it. It's grayed out and disabled.
Why is I've actually never seen that. Okay, give me a moment.
Yeah, the little screen has a red line through it.
Yeah, let me
I'm not sure why. I've been
see if the settings have changed. One moment.
I was planning on just uploading the slides and that's what I did during the dry run, and it worked pretty well. I uploaded a copy to Google Slides already in case it comes to that.
Oh, okay, I see why. The setting for this session, it has it's limited to 2 people that can be on stage to like prevent audience members from coming in. And because of that, the share screen is like a third person. So I think we
You
should
count as my screen. So if you want to leave stage, we could go to the chat and chat there, or
sure. I mean, I think we can
just direct message you, I guess.
We can change the setting. It shouldn't take too long.
Oh, okay, great. I might just turn on the light quickly.
The pleasure of online conferences and live troubleshooting.
Yeah, no worries at all. I'm sure everyone's used to having to start a minute or two late.
Yeah, of course. Okay. I think if I Okay, there we are.
Success.
Disaster averted. All right, that's good to go. We'll just give it a few more minutes. Well, at least 5.
Absolutely. Let people stream in slowly.
And for the people who are already here, thank you for joining. We're just going to wait another 5 minutes or so before we get started.
Professor Vanderlinde, Sean, just to let you know in advance, I'll be handling the Q&A at the end for any technical support.
Perfect. All right, seems the morning coffee is still being made across the room here. But I think I'm sure more people will trickle in as we get started. I'll start the introduction and pass it to you, and we'll take it from there.
Great.
So welcome everyone to our next speaker session today. I'm introducing Dr. Keith Vanderlinde, an experimental cosmologist and long wavelength instrumentalist at the University of Toronto. He spent the first decade of his career studying the oldest light in the universe, the cosmic microwave background, including an 11-month stint in Antarctica operating at the South Pole Telescope. Lately, his work has focused on cosmology with radio telescopes, which are undergoing something of a revolution thanks to the explosion of digital computing power now available. Keith and his team have developed the custom supercomputer at the heart of the Canadian Hydrogen Intensity Mapping Experiment, or known as CHIME, and is leading the digital system design on South Africa's upcoming HIRAX telescope, and is also co-leading the upcoming CORD telescope in Canada. His talk today is titled How to Map a Universe, and I'm so excited to hear more about this. So I'll pass the stage to you, Dr. Vanderlinde, and I'll join the audience here.
Great, thanks very much. Like you said, I'm an experimental cosmologist, which means I build telescopes primarily to study cosmology. Cosmology is probably a slightly different beast from what you've been talking about so far in this conference, because it deals with the universe on the largest possible scales. So what I study is if you zoom out and zoom out and zoom out and zoom out and keep zooming out all the way, you get to sort of the overall global properties of the universe. And that's the stuff that concerns me in my studies. So to start, I thought I would just do a quick tour of how we get there, to put things in context a little bit. So here's Earth, hopefully familiar to everyone. Most of human history has been spent wandering around here, mapping the Earth. In the last 100 years, we've managed to get off the Earth and launched a bunch of satellites. These dots are drawn to scale. These are the low Earth orbit satellites here, and the ring are geosynchronous satellites, things that orbit and stay in fixed position relative to a point on the ground. We're pretty comfortable with that. This is where most space activities happen these days. The farthest any person has ever traveled from home is just to the far side of the moon. This is, again, to scale, showing this ring around the Earth. That is those geosynchronous satellites from the last one. And the distance to the moon is something like almost 400,000 kilometers. And that's the farthest that anyone's ever been. So to see anything farther than that, we really are relying on remote probes of one sort or another, whether we physically send something there to take pictures, or we just look at the light that's coming from there. We aren't doing it ourselves. Of course, we live in a solar system with several planetary neighbors. We're one of the little guys in the local neighborhood. This is the Earth here, and as you can see, Saturn, Jupiter, the gas giants are a heck of a lot bigger, and all of them pale in comparison to the sun, which contains something like 99.8% of the material in the solar system. The other 0.2% are mostly in Jupiter and a little bit in Saturn. The Earth really doesn't really rank on this scale. We're this little dark P here. So already at the solar system scale, we're getting fairly small. To scale, this is the sun to scale. The Earth would not be visible on this scale. The Earth is 1 astronomical unit away from the sun, 150 million kilometers. We're pretty familiar with the local neighborhood. Like I said, all the other planets orbit around the sun. There are these 4 rocky planets on the inside, then an asteroid belt, the gas giants, and into the icy planets farther out. Pluto's on here for historical reasons mostly. But if you keep zooming out past the planets, the 4 inner planets zoomed in here and all of the outer planets there, there's a Kuiper belt of icy objects. And beyond that, there's the Oort cloud, which is largely remnants of the formation of the solar system. That extends out to almost a light year, a very large scale. I want to stress at this point, until the mid-1800s, no one really knew that there was a universe beyond the planets. So this is sort of the largest scale that people thought of when they thought of the universe 200 years ago. In the actually early 1800s, Bessel discovered that you could work out the distance to other stars by looking at them on one side of the sun and then looking at them 6 months later when we're on the other side of the sun, and you can see them move a little bit. Same way if you blink your eye with a finger in front of your face, you can work out how far things are away just through trigonometry. So once we worked out that there were other stars, the universe got a whole heck of a lot bigger. Here's the local neighborhood of stars. The sun, here are Proxima and Alpha Centauri, the very nearby guys. A lot of these names are probably starting to be familiar to most people in the audience from science fiction or from, works of popular culture. Things like Sirius or Wolf 359 show up in all sorts of pop culture things. This is now quite a large scale, right? We're talking 10 light years on this bar here. Now I'm going to keep zooming out. This is still nowhere near the cosmological scale. If you keep zooming out, you can get to a large number of stars in the local neighborhood. This is now 100 light years in the bar. Keep zooming out. We're up to 1,000 light years, and the arms of our galaxy start to resolve themselves. From here out, we're looking at sort of a mix of artists' renditions and data. So everything before this is extremely well measured and known. The density of stars in these arms is less well known. If we keep zooming out, we get to the whole of the Milky Way. And this, again, 100 years ago, was all that people thought was in the universe. The universe, until 1924, was just the Milky Way galaxy. It was thought that we were an island of stars within a universe, an infinite void, effectively. That lasted until Hubble started measuring the distance to these nebulae, which it turned out were other galaxies. He found out that way beyond our Milky Way galaxy, there were other ones. If you zoom out, there are a bunch of small galaxies that are, again, nearby. I see someone putting that in quotes. Yeah, we're now in the hundreds of thousands of light years range. But it's a couple million light years before you get to the next major galaxies, things like Andromeda or the Triangulum. Along with the Milky Way, these 3 make up our what's called the local group of galaxies. This is sort of, we are gravitationally bound together. This is our neighborhood, galactically speaking. if you keep zooming out, the local group now is these 3 dots at the center of my image. And you can start to see other galaxies here. Every dot here is now a galaxy. So we're talking hundreds of billions of stars in each one of these dots. And they clump up gravitationally into clusters, into groups. And if you zoom out even further, into superclusters. These sort of huge, huge, huge clumps. And now we're up to the 100 million light year scale. And we're finally getting to cosmology. Cosmology typically worries about, we say, the 100 megaparsec scale. And a parsec is about 3.7 light years. So roughly the diameter of this sphere, this is the first sort of, you can think of it as a pixel in cosmological terms. This is a unit of space for a cosmologist. And if you keep zooming out from here, this is all well measured. If you could keep zooming out, the universe starts to look something like this, where our local supercluster, Virgo, is this dot in the middle. And for billions of light years in every direction, there's this sort of almost spongy fibrous structure to the way that matter assembles. And this is what I'm talking about when I say how to map a universe. We're worried about this sort of a scale. Now, this fibrous sort of spongy structure is something that we call the large scale structure of the universe. It's something that cosmologists study computationally mostly. We make giant simulations in computers, throw in lots of matter, and just run the clock forward and see what gravity does. And what gravity does is forms these huge structures. Now, this is actually showing a map of dark matter, which is about 5 times as common as regular matter. It's simulation only. Of course, dark matter is dark. You can't see it. But in each one of these little light spots, you might expect to see a dozen, 100, or 1,000 galaxies, depending on how big a sort of knot of material there is there. And mapping out this large-scale structure of the universe is something that a lot of cosmologists worry about today. And particularly, it's one of my major interests in cosmology, trying to map out the large-scale structure. So how would you do that? The way that people have done it traditionally is with galaxy surveys. You go out and you measure where all the galaxies are. So you go and get a large telescope, find a galaxy, figure out how far away it is, and do that hundreds of thousands of times and put them all down on a map, and you end up with something like this. And you can see that when we do that, this is actual data from 20 years ago almost, from the Sloan Digital Sky Survey, you get this fibrous large-scale structure. And the way that it behaves, the reason we study this is because it tells us all sorts of things about the constituents of the universe, about dark matter and about dark energy and about the thermal history and how it's expanding and just everything that's going on these large scales comes out of these maps of structure. But at some level, we're also just explorers, right? We're interested in trying to find out what's out there in the universe and to nail down our position in it, get our place in the wider cosmos. Now, this only works for the first few, well, maybe gigaparsecs. It's hard to get really, really, really far out into the universe. And you can see that it's sort of fading out. And that's because as they get farther away, these galaxies get fainter. It gets harder to find spectral lines, so emission lines that you can tell where exactly they are. And it just gets extremely hard to do this sort of galaxy survey. I have a colleague who describes this nicely. He says it's like trying to make a map of the Earth where you're wandering around and calculating the very careful position of every grain of sand on the whole planet. That's sort of what you're doing when you're going to and trying to find all of these little galaxies. If you go back a couple, you'll remember that I said in each of these large clumps, there are dozens to hundreds to thousands of galaxies. So identifying all of those galaxies is sort of wasteful. It's like trying to map out all of the grains of sand on the planet to get a map of Earth. It's just not how we do it. So instead, we blur things out. We look for some other way that we can make a measurement, stand farther back, defocus, use a different color of light, and map out the coarser structures of these things. And that's the idea behind a lot of my work, that rather than trying to map out the really fine detail on the left here, I blur it out, just like with this sort of sand footprint in the sand. You can perfectly well measure that there's a beach without knowing every grain of sand's position. So to do that, we have to look a little bit beyond traditional astronomy. normally, when we think about looking at things, looking at light, we think of all the different colors that make up the rainbow. But of course, that's visible light. This is a tiny fraction of all the colors of light that make up the rainbow. At higher energy, you have ultraviolet, X-ray, and gamma rays. Lower energy, there's infrared, microwaves, radio waves. And it's these lower energy lights that I tend to work in. Just to show you what the sky looks like. This is the visible sky, so visible light. And just to say, I'm not saying that the universe is some sort of egg-shaped thing. I'm taking the sky overhead and just unwrapping it and putting it down in this funny projection, just like any map will project somehow. So the gamma ray sky looks like this. You mostly see our galaxy running through the middle, and all of these bright little dots. Those are from supermassive black holes in other galaxies. The X-ray sky is very hard to see. The atmosphere blocks X-rays and gamma rays. So you have to do all these from satellites. Same with the ultraviolet sky. UV sky is extremely hard to map just because the sun is so incredibly bright in UV. You basically are blinded anywhere you look. The visible sky is the familiar one that you see if you look up at night. The infrared sky is now something that people are actively researching. You can see stars better in infrared light, and you can see planets much better, exoplanets much better. So like the JWST, James Webb Space Telescope, is an infrared telescope that's going to be doing fantastic things in the near future in infrared. I'm going to jump over over microwaves for a minute, because radio waves is what I primarily work in. And that's how we make these images that are blurred out. The problem is still that it's extremely faint light. So you tend to need very large telescopes. This is an enormous telescope, right? This is 300 feet across, 100 meters. You can see cars and a building at the bottom for scale. You need this kind of telescope to get the sensitivity that you need. But unfortunately, megastructures like this are, one, super expensive, and two, things can go wrong. And that dish actually collapsed in a storm 30 years ago. They rebuilt it, but it's an extremely expensive prospect. So nowadays, people try not to build megastructures like that. Instead, telescopes today look something like this. This is a modern radio telescope. It's a bunch of antennas just thrown on the ground in Western Australia. And the idea here is that rather than using a giant mirror to focus light, we understand the physics of light perfectly well. It's an electromagnetic wave. We can apply math to it to manipulate it however we want. So we just record the electromagnetic wave and then do everything else in a computer. So we shovel the telescope essentially into a computer. And that's what we do on the telescope that I work on most of the time, this CHIME telescope, the Canadian Hydrogen Intensity Mapping Experiment that was mentioned. It looks crazy. All modern radio telescopes look slightly crazy because we don't focus things with mirrors. We focus things, well, this is a one-dimensional mirror. It focuses east-west, but not north-south. And instead, we use a supercomputer backend to focus things. Building things like this, it looks a little different. You have hundreds of kilometers worth of cabling that you have to plug in, and everything has to be right because we're carrying all of these signals from the deep cosmos back and forth between electronics components and into the supercomputer backend. This is what that supercomputer looked like. This is something that we built in my lab at U of T. It has 1,000 of the top-end GPUs, video cards, that power the whole thing. So we just took knowledge from other industries, from video gaming, really, and applied it to making images of the universe instead of making images of whatever video game world. And with that, this is to give you a sense of the scale we're talking about what we're mapping. So that earlier map of hundreds of thousands of galaxies is down here from SDSS. People have mapped out chunks of it in this white area, but the region of sky that CHIME is looking at is this huge volume farther out. And this is what it does. It makes the largest ever map of the universe. So you might ask from that, great, that seems promising. That's one way of mapping it. But how far can you see? How big is the universe? And just as a quick aside, we have to say light has a few properties. It's extremely fast. It's the fastest thing there is. It runs at 300,000 meters per second. But it's not instantaneous. 300 million meters per second, sorry. Light from the sun takes 8 minutes to get here. When you get to these large scales, there are macroscopic delays between when light is emitted and when it gets to us. That means that when we look at the sun, we're seeing light that it gave off 8 minutes ago. We're seeing what the universe was like, what the sun was like 8 minutes ago. I'll get to the questions at the end, but please keep typing them in the chat. I'm just watching those come up. So on larger scales, that's a bigger issue. If we look at Proxima Centauri, we're seeing what happened 4.2 years ago. It's the closest star there is, and we can't see what happened to it in the last 4 years. We are looking at a 4-year-old picture of it. Similarly, if Proxima Centauri is little aliens and they're looking at us, they're watching us argue about this Oumuamua traveler that we had zip through 4 years ago. They don't know that we have coronavirus. They don't know anything about the last 4 years because the Earth that they see, that stuff hasn't happened yet. Now, on larger scales, that's a much bigger deal. The nearest galaxy, remember I said, is 2.5 million light years away, this Andromeda galaxy. We're looking at a picture of it that's 2.5 million years old. And similarly, if there are incredibly capable aliens there that have gigantic telescopes looking at the Earth, they're looking at an Earth that doesn't have people on it. They're looking at an Earth that just evolved the Homo genus, that has Homo habilis starting to wander around. They are seeing a very different thing. So as you look farther away, you're seeing farther and farther back in time. And how far can we see? Well, we don't actually see an edge. There is no known edge to the universe because before we get to an edge, we get to the beginning. You see far enough back in time that you see the start rather than getting to some edge. As far as we know, the universe is infinite, but the observable universe is the portion of it that has had time to show us anything. That oldest light in the universe is called the cosmic microwave background. It's shown here. This is a plot of the age of the universe. We live out here at 13.8 billion years. And as you look farther and farther and farther and farther away, eventually you get to this cosmic microwave background. It really is a wall of fire at the beginning of the universe from when the universe was incredibly small, hot, and dense. And this is why I skipped over that microwave image. If you look at the sky in microwaves, this is what it looks like. This is not a printing error. This is, honest to God, what the sky appears. If we could see microwave light with our eyes, it would just be a strong glow. The entire universe is full of this light, which is just traveling through. This picture actually won a Nobel Prize back in the 1960s for the discovery of the cosmic microwave background. And you might wonder, why does anyone bother studying this? It's just gray. Well, if you turn up the contrast by about a factor of 50,000, you can start to see things on it, structure on it. You can start to see hot and cold bits in the early universe. You can start to see that this is a picture of the early universe. This is this funny green and blue thing that you're looking at. And it's the equivalent of starlight. It's from long before there was starlight. And it's the glow left over from the universe. So this makes a nice, beautiful shell on the outside of the observable universe, and it's the farthest we can see. We can't see past it. It's a plasma. It blocks all light. And that really sets the boundary on the observable universe. So that's the chunk of sky that we're interested in mapping out. And that's another thing that I have studied using the South Pole Telescope. The South Pole Telescope is a 10-meter radio dish located at the geographic South Pole, or about 1 kilometer away. And it's built to look at this cosmic microwave background. This is a picture that I took when I was down there. As mentioned, I spent a year down at the South Pole running that telescope, mapping out this cosmic microwave background. And the reason that we're down there, there are sort of 3 main reasons. One is that it's extremely dry. Water absorbs and emits microwaves. It is opaque to microwaves. Visual light goes right through water, or at least it goes fairly well through. But microwave light is absorbed. That's why microwave ovens work, right? It shines a bright light of microwaves at your food, and the water in your food heats up from it. But at -70, there's very little water vapor in the air. People in Canada are pretty familiar with this. Things dry out in the winter. It's also extremely high up at the South Pole. The bedrock is actually about sea level, but we've got 3 kilometers of ice sheet on top of it, and you sit on top of the glacier. So you're nice and high up. You're above a lot of the atmosphere. You've got virtually no moisture between you and space. And you get a nice clear view of this microwave light. The other nice thing about the South Pole is that it only has 2 seasons. It has day and night. The sun rises on March 21st and rises on September 21st and sets on March 21st. And that's it, which means there's much less turbulence in the air. You don't get this daily warming and cooling cycle that we have in the rest of the planet. It's nice, stable, calm air, high up without any moisture, and you get a beautiful view. And that's why SPT is down there. It studies the oldest light in the universe, this cosmic microwave background. I have some more photos of that, so I'm happy to show them during the Q&A, but I'm going to try to wrap up quickly now to sort of summarize what we're doing to map the universe. This is my picture of the whole observable universe. The CMB is this outer ring, that cosmic microwave background is this dark ring. That's as far as we can see. Somewhere behind that is the actual Big Bang. But we can't see it, like I said, because the CMB is a plasma, you can't see through it. For a long time, a large portion of the universe, there were no stars at all. Stars hadn't yet formed. Stars only exist inside this blue circle. So if you want to create a map of this whole universe, you can't just look for starlight from galaxies. That will only work inside this blue circle. That SDSS image that I showed is here. It's kind of amazing that we're already mapping out, a macroscopic fraction of this universe. SPT is looking at this cosmic microwave background, and it's acting as a backlight to everything else. So as it comes to us, we actually see it interact with other matter, and we can map out portions of the universe that way. And CHIME sees this huge chunk, or will eventually see this huge chunk that I showed a simulation of earlier, and map out this. Now, that's great. We're getting there. But if you want to map out the whole thing, what do? Well, inside this blue circle, you can always look for more starlight. You can build more powerful, more sensitive telescopes. But outside, the only thing that there is neutral hydrogen and neutral helium floating around. So you really need to build a telescope which sees hydrogen, just gas. And it turns out that that's effectively what CHIME is doing. CHIME is just mapping out hydrogen in this range. That's how we're blurring out our vision. We're just looking for the bulk emission, the bulk glow from hydrogen inside galaxies over this range. And if you build a larger telescope, something like a square kilometer on a side, a kilometer on a side, a square kilometer total, you can get access to this larger region with what's called hydrogen intensity mapping. So I think I'm already at my half hour. I'm going to wrap up there and say, if you want to map a universe, you can map most of it with a good chunk of it with stars. Then it gets too much detail, and you need to start breaking it down into other things, like radio light, like this hydrogen mapping, or like microwave light to see the edge of the whole thing. So I will stop there and take questions. And if people want to see South Pole photos, I can put a couple of those up. I guess I will just start going through the questions on the side. Great. The darker region, is that still visible? I believe that was on this slide. Cameron, is that right? Or was I on a previous slide? Okay, this is all within the observable universe. The observable universe boundary is substantially beyond this, sort of 2 or 3 slide widths away. So yes, all of this is observable. The darker bits are, so the color coding here, lighter just means more mass, lower means less mass. So there's more material where it's lighter, more galaxies. So if you were just to go out and make a map of starlight, it would look something like this. The dark bits are what are called voids, where there's very, very little matter. They're hundreds of millions of light years across with virtually nothing in them. They're an interesting aspect of the universe. Okay, by not focusing, do you lose optical resolution, or is that completely compensated by the back end? It's actually even better than completely compensated. If you work through the quantum mechanics of how light focusing works, sorry, I'm just trying to flip through to find the right slide. Something like this. it's slightly suboptimal. You are not doing the best possible version of focusing if you just use a lens or a mirror. You can do a little bit better for teasing apart the separation of objects, which is how we usually describe resolution. How close can things be before you can't tell them apart? But the radio version, where you do all of this computationally, is formally optimal. So you get all of that resolution back, and you do even a little bit better than you would think you could do. Just guessing here, but perhaps this gets more difficult if the rate of expansion is not linear. Yeah, so that's a great question. I didn't even go into one of the complications. So let's go back to, say, yeah, here. This gets harder for a few reasons as you look farther and farther and farther out, partly because light is distributed over more area. Things are just harder to see when they're further away. They're fainter. Less of the photons get to you. But as sort of implied by Cameron, I didn't even mention that there's a huge complication on this, that the universe is not static. The universe is expanding moment by moment. Space is getting bigger, which means distances get complicated. As light takes billions of years to travel to you and the universe expands while it's traveling, the light changes. You have to deal with the changing notion of distance. These galaxies are currently a different distance from each other than they were when we measured them. So there's this problem that you're measuring an evolving system. Luckily, the math is pretty well understood. It's pretty straightforward, so you can back it all out. It does get more complicated than you might otherwise expect, yes. And that rate, as sort of hinted at, it's not linear. It started out very, very quickly, and then it slowed down for a while, and now it's accelerating again. So the expansion of space-time is one of the big things that people are studying in cosmology, and it's one of the big reasons we make these maps. These sort of large-scale structure maps, they tell us about that expansion history in the universe, because as we're looking farther away, we're looking farther back in time. We can start to measure how the universe has expanded and where it's expanding, in what it is doing in the future. I should also say, it's not that it's expanding into something. It's not that there is a nothingness outside the universe that it's growing into. Each little chunk of space gets bigger. That's all the expansion is, that every little unit of volume is growing over time. It's not that things are moving into new space. It's that space grows over time. How sure are we of dark matter's existence? Is there a possibility that it doesn't exist, but our estimation of everything else may be incorrect? So dark matter, I think, is about as certain as anything in science these days. Dark matter, just to be clear, what dark matter is, it's stuff where most of its energy is in mass. Regular matter is the same. Most of my rest energy, we say, is in mass. This is the E equals mc squared thing from Einstein. In the case of, say, light or other particles like that, if we accelerate particles to really, really, really high speeds in particle accelerators, then most of their energy is in its kinetic energy. It's not their rest mass. So matter of any sort is stuff that has mass, essentially, something that has weight to it. Dark matter is just something with mass that doesn't care about light, that doesn't interact with light. I interact with light all the time. I absorb it, I emit it, I reflect it, I heat up from it. I do lots of things with light because I'm made of regular matter. Dark matter just doesn't care. Light goes right through it. Light does not interact with it in any way, shape, or form, which is why you might say, sure, but then how do we know about it? It still has mass, so it interacts gravitationally. We're very sure of at least one type of dark matter we know because we have actually detected it. Neutrinos are formally dark matter. Neutrinos don't interact with light. The sun emits them by the billions. They're traveling through this room, through me, by the trillions every second. And we have built neutrino detectors. You can get them to interact. Most of the dark matter that we see out there is not compatible, or that we think we see gravitationally by the impact of gravity. It's not compatible with something like neutrinos. We think there's another type of dark matter out there. But dark matter as a whole seems very certain. There's definitely something that has mass, which is out there, which is interacting in a way that we can't see with through some interaction with light. That's dark matter. I'll say dark energy is the much larger contribution to the universe, the thing that we think is causing the name that we give to the thing causing the accelerating expansion of the universe. And dark energy, I would say, is much less certain. It's something that's been around for 25 years. Sort of 1998 is when it was discovered, or at least there was strong enough evidence for people to add it to their default model. I do think it's very well accepted. It's extremely likely correct, but it wouldn't overturn decades and centuries of thinking if we found some other model that did a better job explaining it. Yeah, it is in the nominal models everywhere, but this is how science works. We make models and we test them, and then some better explanation comes along and we use that as the new model instead of the old one. Is it possible to observe something using quantum entanglement? I imagine a point cloud of quantum particles showing a somewhat 3D object. That's a good question. I am not a quantum metrologist. I would have to think extensively about that. So it definitely is possible, but not all things produce entangled particle states that you'd be able to use meaningfully. People do entangle photons for measurements on Earth and use them to probe some object. And actually, that when I mentioned that with the supercomputer, you do even better in resolution than you would do with a normal mirror or lens. One way that people get around that with mirrors and lenses with optical systems is through entangled photons, and they use them in measurement processes. This is an active field of research right now, trying to figure out how to get away with that. You ask because the rate of expansion is unfortunately faster than the speed of light, hence having an observable universe, and quantum entanglement could bypass needing to receive light data. Yeah. So entanglement, as far as anyone's been able to show, can't carry information faster than the speed of light. It can carry random process couplings faster than the speed of light. It's not clear that you can actually use that to transfer any information from one spot to another. I think still very experimental and theoretical and not super well known. So I hope so. I wouldn't bet on it. There are other things that people talk about doing to try and get beyond the edge of the universe, beyond event horizons, trying to understand, say, the inside of black holes or the outside of the observable universe. But those are, again, purely theoretical. There is zero observational evidence of any of that. And as an experimental cosmologist, I hold off judgment until there's some sort of demonstration, a measurement that you can point me at. Okay, I think I've worked my way through the questions. If people have any more, feel free to post them. Otherwise, I'll just throw up a couple of photos of the South Pole as a little travelogue. So at the South Pole, like I said, there are only 2 seasons. There is daylight and nightlight, or daytime and nighttime, summer and winter. Summer, which is during the northern winter, it's at the South Pole, so seasons are reversed. Summer runs from about mid-November to mid-February, and that's the only time you can get in or out. In the winter, it's too cold to land planes, and the South Pole itself is several thousand kilometers from the coast, so you can't really easily get in on foot. People do it. People ski in. That's certainly how the original explorers made it, and there is a traverse with a convoy of tractors, effectively, every year. But for the most part, everything there comes in and goes on a plane. What did I do there? I was running this telescope, the South Pole telescope, that's looking for this cosmic microwave background data. I went down just after I finished my PhD to run it for a year. So you can only come and go in the summer. Eventually, it gets too cold to run things and to run planes. So the last plane takes off and leaves. all the planes in and out of the South Pole. The South Pole Station it's run by the United States government, and they contract all their flights from the U.S. Air National Guard, I think, from New York. And there are these really cool ski planes, right? There's no runway. There's a skiway where people pack down the snow a little bit to get in and out. And they leave people behind. They leave people behind for the simple reason that machinery breaks down when it's minus 70. Things don't work super well. People keep going. They just put on another jacket, put on another thicker pair of socks and more mittens, and you can keep going. What is the significance of the telescope in Antarctica? Why build it there instead of somewhere warm and lacking light pollution? So I said this earlier, that it's looking for microwave light. To see microwaves, you need to go somewhere really, really dry. It's not light pollution that we're worried about so much as moisture. And moisture is significant anywhere that you go that's warm. Warm and on Earth, you're going to have moisture. Even in the driest deserts in the world that are hot, they're much, much, much more humid than the South Pole. The South Pole is the driest. Well, Antarctica is the driest continent on Earth, and the South Pole is near the driest part of the driest continent. So it's almost the driest place on the planet, which gives you the clearest view looking at microwave light. You're right, it's a huge pain in the behind to go down there, but there's a very good motivation. The sun spirals around during the summer, and then it slowly lowers until it eventually goes below the horizon, and it spirals below the horizon. So for weeks at a time, as you're there, you just see this sun drifting along the horizon. Once it finally sets, here's the telescope that I was operating in the lab that's next to it. This is about 1 kilometer away from the station, and you have to walk out there a couple times a day in the minus 70. To make sure you don't get lost, they set up a flag line, because for most of the time that you're down there, it's going to be very dark. You just listen for the flapping of the flags in the wind. They tend not to tie ropes, because the ropes can fray and break in the winds and lead you off into the middle of nowhere. And when it's dark out, you don't want to get lost, because it's hundreds of kilometers across flat, barren ice before you hit anything else. And particularly when storms come up, it can be extremely hard to see anything. A storm at the South Pole is mostly wind. You occasionally get precipitation, but mostly it's just blowing around, and it blows up the snow from under you. You get there are upsides to being down there. Like the aurora australis are spectacular. They're the same as the aurora borealis, but borealis means northern, australis means southern. You're at the south. They have fun things like this wind rose that has just north on all 4 points, because every direction is north. When you're asking for directions, you tend not to give it in north, south, east, west. Instead, we make up what we call grid north, south, east, west. This is the station that people live in. This was completed in 2008, the year that I was there. This is the 3rd station that they've deployed down there, actually. There have been a couple before it. Again, beautiful auroras that are overhead all the time. The walk to work looks something like this. You're trudging along the snow in the minus 75 degrees, but you can tell what time it is because the galaxy is rotating overhead, and it's the clearest view you'll ever experience in your life. And there's this bright aurora that runs horizon to horizon overhead. So, if you can handle the cold and the dark and the isolation for months at a time, it's a beautiful place to be. And this is what work looks like. You sort of hang out under the stars, looking at auroras, fixing telescopes in ridiculously cold weather. So I'm at the quarter after. I should probably stop there. If anyone wants to ping me about these things, I'm certainly easy to find online.
Thank you, Evan, for attending our talk on mapping the universe, and special thanks to Professor Vanderlinde for helping us learn more from his expertise in experimental cosmology at our conference here today. The next imminent event is Developing a Commercial Spaceport in Canada by Steve Matier at Maritime Launch Services. Make sure to check your schedule for the link to that event. Thank you again to Professor Vanderlinde for sharing your expertise.
Thanks. Bye, everyone.